Hello everyone, welcome back to our MOOC on Zero Knowledge Proofs. I'm Yupeng Zhang, and today I'm going to talk about SNARKs based on linear PCPs. So first, I want to remind everyone about SNARKs we've learned so far in this table. In lecture 6, I introduced this classical protocol of the KZJ polynomial commitments based on bilinear pairing. Combine it with the Planck IOP in lecture 5 or the interactive proofs in lecture 4, we end up with SNARKs with a trusted setup. And these constructions tend to have a small proof size in practice. And in order to remove this trusted setup, I've talked about schemes based on discrete logarithm. And those include bulletproofs, Dory, dark, and hierarchs. And we also have SNARK implementations based on these polynomial commitments, such as Halo 2. During the past two lectures, we also introduced the schemes building SNARKs based on error correcting codes. In lecture 7, we talk about schemes based on linear time encodable code and Merkle hash trees. And those include breakdown and array. And in the last lecture, Justin talked about this interesting line of research building SNARKs based on resolvement code and the Frye interactive oracle proof schemes. And these schemes can actually further reduce the proof size from a square root to polylogarithm. And they include Stark, Aurora, Fractal, Virgo, and so on. The goal of this lecture is to talk about another technique to build SNARKs based on the so-called linear PCP. And this technique was actually proposed before those polynomial commitments and polynomial IOPs, and has been used to construct the earliest implementations of SNARKs. So it's worth to spend this lecture to study the details of the constructions. So to briefly show you the properties of these constructions, on the positive side, these SNARKs tend to have very short proof size in practice. For example, in this construction proposed by Jens Gross in 2016, the proof only consists of 3 group elements. And in practice, it's only about 100 to 200 bytes. So that's actually the shortest proof size among all the SNARKs we are learning in this course. And for a similar reason, these SNARKs also have very fast verifier time. Again, in this construction of Gross 16, the verifier only needs to check one pairing equation using 3 bilinear pairings. And in practice, it only takes less than 1 millisecond to do it. And in terms of disadvantages, the prover time of these SNARKs tend to be relatively slow in practice because they require both FFT and group exponentiations. And the size of these computations are linear in the size of the circuit to prove. And because of that, they're usually slower compared to schemes based on, for example, error correcting codes. Another major drawback of these constructions is that they require a circuit-specific trusted setup. So there has to be a preprocessor to perform a trusted setup with the trapdoor and delete this trapdoor completely after the setup phase. And these schemes have to do this trusted setup for every computation you want to prove. And this may not be desirable for some applications in practice, and because of that, this is sometimes called preprocessing SNARKs in the literature. And this is different from the SNARKs we've seen so far. For example, the Planck system that requires a one-time universal trusted setup, and also other schemes without trusted setup at all. So before going into the detailed constructions of these SNARKs based on linear PCP, I want to briefly introduce the history of this line of research. So in the early days, the original constructions of SNARKs were proposed in these 2 seminal papers by Killian and Mikali. And in these 2 papers, they combine the classical protocol of the probabilistically checkable proofs, PCP, with Merkle trees. And the constructions of SNARKs are actually asymptotically optimal up to polylogarithm factors. They do not require any trusted setup, and they have a succinct proofs and verifier time. So in theory, they're actually very good. And also in this paper by Mikali in 2000, he actually applied the Fourier-Shamir transformation to remove the interactions in this construction and get a non-interact argument of knowledge. But unfortunately, they don't lead to efficient SNARK systems in practice, partly because of the heavy mechanism of the PCP. And to the best of my knowledge, I'm not aware of any concrete efficient systems implemented based on this PCP plus Merkle tree. So motivated by this problem, there is this line of research constructing SNARKs without the classical PCP algorithm. And this line of research was started by Ishai, Kushlevsky, Ostrowski in 2007. And in this paper, they proposed this concept of a linear PCP. And they built a scheme combining this one with a homomorphic encryption to get a SNARK with short proofs. But unfortunately, the poor time is quadratic in the size of the computation. And later, Jens Gras proposed the construction of SNARKs based on bilinear pairing in this paper in 2010. Although it's not directly built on top of the construction of the linear PCP, it can still be classified as a linear PCP in this model. And in this construction, it applies the bilinear pairing, which is kind of the ancestor of the SNARKs I'm going to talk about today. But unfortunately, the size of the global parameters and the poor time are still quadratic in this construction in Gras 10. And later, the scheme was further improved by Helger Lippma in 2012 with a technique called progression-free sets. With this technique, he improved the size of the global parameters from quadratic to quasi-linear. But still, the scheme has a quadratic poor time and does not have a efficient implementation in practice. And finally, a big breakthrough in this line of research was actually proposed in this paper by Gennaro, Gentry, Parno, and Rykova. And there they proposed this very beautiful construction of a quadratic span programs and quadratic arithmetic programs that reduces the poor time and the size of the global parameters from quadratic to quasi-linear and linear in practice. And that leads to efficient instantiations and many systems in practice. And this is the one we are going to talk about today, the QAP. And after that, this line of research has led to many new techniques and efficient constructions of SNARKs. And they were usually before the invention of these polynomial IOPs and polynomial commitments we've talked about before. And here I'm just listing a very small subset of papers, and there are many more papers with both theoretic contributions and concrete efficient systems for different applications. And there's a very long literature building SNARKs based on linear PCPs and QAPs. And in this short list, there are several papers I want to highlight. For example, this one by Parno, Gentry, Howell, and Rykova. They proposed this system called Pinocchio. That is one of the earliest efficient constructions of SNARKs, and is the one that I'm going to talk about today. And here we have SNARKs for run-based computations, such as SNARKs for C and TinyRun. And we also have the recursive SNARKs of cycles of Yupeng curves in this paper by Ben Sassong et al. And we also have this famous construction for Gras 16 with the smallest proof size of only 3 elements. And that it has been widely used in practice for different applications. And another line of research has built this SNARKs based on the original linear PCP construction. And in these 2 papers by Sally et al., they have the SNARK systems called Ginger and Pepper. And that was also one of the earliest systems of SNARKs. And also in this paper by Bitansky, Kiasa, Ishai, Ostrowski, and Panis, they actually unifies this line of research under the framework of linear interactive proofs. And these QAPs and linear PCPs are actually instantiations in this framework. So that's a brief introduction of the history of this line of research on linear PCPs and QAPs. So in order to understand the construction of these SNARKs based on linear PCPs, I'm going to follow this common paradigm for building efficient SNARKs again. So recall that in order to build the SNARKs for general circuits, we really have information theoretically secure component And this time it's going to be this linear PCP or quadratic arithmetic program. And then we are going to compile this information theoretic secure component to concrete efficient SNARKs with short proofs using an appropriate cryptographic tool. And this time we're going to use the bilinear pairing to do it. And this is actually different from the polynomial IOPs and polynomial commitments we've learned before. So then we will have three segments of this lecture. In the first part, I'm going to talk about this classical construction of a QAP, quadratic arithmetic program. In the second part, I'm going to show you how to construct an efficient SNARK with a constant size proof from the QAP using bilinear pairing. And in the last part, I'm going to talk about variants of these SNARKs in this framework of linear PCP. Those include the support of R1CS, rank 1 constraint system, and also the variants of a Groth 16 with 3 group elements in the proof, and also how to achieve zero knowledge in these constructions. So let's start with the QAP. So recall that our job is to build a SNARK for proving circuit satisfiability, which means that given an arithmetic circuit C defined over a finite field with addition gates and multiplication gates and an output Y, the prover P is trying to claim that he knows a witness W such that C of X comma W equals to Y, where X is the public input known by the verifier. And for simplicity, let's ignore this public input for the time being and assume that all the inputs are secret, held by the prover. So the prover is trying to convince the verifier that he knows the satisfying assignment, the input and values of the circuit, such that C of W equals to Y. So that is the setting and the problem we are trying to solve. So next, I want to reintroduce this concept of a transcript or the trace of a computation or a circuit. So here I'm showing you an example of an arithmetic circuit with these addition gates and multiplication gates and this set of values. So the trace just means that the prover is going to evaluate this entire circuit and takes the values on all the wires. And for example, this is exactly the transcript defined in lecture 4 for interactive proofs. That is the value of every gate, including the inputs. And then for interactive proofs, Justin talked about how to construct the sum check and multivariate polynomials representing the addition gates and multiplication gates, and also the transcripts of this computation, and how to use the sum check protocol to check the correctness of this evaluation. Similarly, in lecture 5, when Dan was introducing this Planck IOP, he also defined a trace of this computation, but it's actually slightly different from the interactive proofs. Instead of just taking the value of every gate, it is actually defined as the left input, right input, and output of every gate. So there are some redundancies of this definition of the trace, because one wire can both be the output of one gate and also the input of another gate. So it's actually slightly larger than the size of the value of every gate. But still, it is derived from the evaluations of the circuit. So that's why we still call it the transcript or trace of the computation. So following the same ideas, we are going to define the transcript of QAP for this lecture. Again, it will be slightly different from both interactive proofs and Planck. So this time, we are going to define the trace as the input plus the output of every multiplication gate. And we are going to ignore the output of addition gates this time. So to show you on this slide, so we are going to remove the labels for the output of these two addition gates and only count the output of every multiplication gates here together with the input. So that is the trace we are going to talk about, we are going to use in this lecture. So again, it can actually be derived from the circuit evaluation. So essentially, there's no big difference, but in terms of the formal definition, it's slightly different from the interactive proofs and the Planck IOP. So once we do that, we can actually represent this transcript or trace as a vector. So we can just do this in any predefined order, for example, just following the topological order of the circuit evaluation. We have the 6 inputs, 3, 2, 1, 7, 5, 4, and then the internal wires 6, and then the outputs of the modification gates 48 and 72. And also for simplicity, I'm assuming that the gate before each output must be a modification gate. So that is the transcript of this computation for QAP. And then another thing to introduce is that very naturally, we're also going to label these gates in the circuit. Again, we only care about the modification gates for QAP. And we are just going to label them one by one. For example, we have gate 1, the modification gate here, gate 2, and gate 3. So we have 3 modification gates, and the trace of this vector with 9 values in the circuit, with 6 inputs and the 3 outputs of the modification gates. With that, the next concept I want to introduce is this selector polynomials. So that is the key component to reduce the problem of a circuit satisfiability to a polynomial equation, which is essentially the quadratic arithmetic program. So let's basically spend most of the time of this segment to understand what is the definition of this selector polynomial. So I'm going to first define a set of polynomials called LIX. And how can we define this? We are basically asking this question. Is each Ci in this trace of the computation the left input of gate J for every J equals to 1, 2, and 3 for all the gates? If the answer is yes, we are going to put 1 there. And if the answer is no, we are going to put 0. Okay? And here, for your convenience, I'm basically labeling these values in the computation trace of this circuit as C1, C2, all the way to C9. So then let's take a look at an example of L1x. What is L1x? So then we are asking the question, is C1, this value 3, the left input of gate 1? Well, the answer is yes. This 3 is the left input of gate 1, the multiplication gate. So we put 1 here. And is C1 the left input of gate 2? The answer is no, so we put 0 here. And then finally, is C1 the left input of gate 3? The answer is again no, so we put 0. So we have a vector 1, 0, 0 of size 3, the same as the size of the number of multiplication gates. So then the way to define this L1x is through polynomial interpolation at a known set, capital omega. So with this set, we want this polynomial L1x to evaluate to 1 at, for example, omega, and evaluates to 0 at omega square, and evaluates to 0 again at omega to the cube. So in this way, for any predefined distinct set of values, we have a unique interpolation of the polynomial, and we can actually compute a polynomial L1x with degree 3, assuming that is a monic polynomial, meaning that the leading coefficient is 1. So there is a unique degree 3 monic polynomial with these 3 evaluations. And up to this point, everyone should be familiar with the definition of roots of unity. This is for the convenience of polynomial computations using the FFT algorithm. But so that is why we set this set to be the powers generated by the root of unity. But for the algorithm to work, you can actually, for the product to work, you can actually use any set with distinct values. Okay, so that is how we define this polynomial L1x using the polynomial interpolation. Then similarly, let's take a look at L2x. Is C2 the left input of each gate? Right? Then this C2 is the wire here. It is not the left input of gate 1. It is the right input. So we put 0 here. And again, it's not the right input of gate 2, and it's not the right input of gate 3. So we have a vector of 0, 0, 0. And we are going to interpolate this polynomial using the fact that the evaluations are all zeros at these 3 points. And note that this L2x is not a 0 polynomial. You can actually interpolate the polynomial with these 3 values as the roots. It is actually a unique degree 3 monic polynomial. So similarly, we can do it for every Ci and get the selected polynomial of Lix for all I. But another interesting case I want to highlight here is for L3x. So we are asking, is C3 the left input of gate J? So it is this wire. Apparently, it is not the left input of gate 1, it's not the left input of gate 2, so we put 0 and 0 there. But the rule to define whether it's left input or not when we have an addition gate is that the values should go through this addition gates and connect to the multiplication gates. So in this case, because both 1 and 7 are actually inputs to this addition gate, and the output of this addition gate is the left input of gate 3. So because of that, we count them as the left input of gate 3. And because of that, we are going to put 1 here, denoting that C3 is the left input of gate 3. So that's how we take care of wires related to addition gates. And you're going to understand why we're doing this in the very next slide. So then we are going to interpolate the polynomial using the evaluations of 0, 0, and 1. So that's how we get L3x. And we're just keep doing that one by one. And here's the table summarizing the evaluations of all these Lx, from L1x all the way to L9x. And the evaluation should be these vectors at these 3 points. And we can interpolate these polynomials and get the unique polynomials of degree 3, assuming the leading coefficient is 1. So that's how we define the Lix. Then you may wonder, what's the properties of these polynomials? Why they are called selector polynomials? And here's the reason. So again, I'm listing this table with the evaluations and vector, and I'm going to define a capital Lx polynomial as the summation of Ci times Lix for every I, and multiplying each value in this trace, the vector, with the corresponding Lix and sum them up. So once we have this capital Lx, what is the property of this polynomial? Well, let's evaluate it at different powers of the root of unity. So what is L evaluated at point omega? Well, then by the definition of these Lix, right, we need to evaluate them at point omega. And basically, we are looking at the first column in this table. Because by definition, they're specifying the evaluation of L1x, L2x, L3x, and all the way to L9x at the point of omega. And as you can see from the table, there's only one non-zero value in this column, and that is L1 omega. Because of this property, there will only be one non-zero term in this entire summation. That is C1 times L1 omega. That equals to C1 itself, which equals to 3. All other values will become 0 because of the evaluations of these Lix at omega. So in this way, we are selecting C1 out of this big summation when evaluating L of x at omega. And then what is C1? It's essentially the left input of this multiplication gate 1. Right? So because of that, the property of this capital Lx is selecting the left input of gate 1 when evaluated at omega. So similarly, let's take a look at what is L evaluated at omega squared. Then by the definition of these Lix, we are essentially looking at the second column of this table. And again, there's only one non-zero term in this entire column, and that is L7 omega squared. Because of that, in this big summation, there will be only one non-zero term again, and that is C7. Right? So we are computing C7 times L7 omega squared, that is C7 itself, equals to 6. And what is this 6? That is basically the left input of the second multiplication gate here. Right? So we are selecting the left input of the second gate out of all these values from the trace. And finally, what is L evaluated at omega to the cube? Then we are looking at the third column in this table. And note here that there are actually two non-zeros in the third column. that corresponding to L3x and L4x. Because of that, we are selecting C3 and C4 and add them up together because of the summation in this equation. So L of x evaluates to C3 plus C4 at point omega to the cube. And if you take a look at this circuit, that's exactly the left input of gate 3. That is C3 plus C4, that equals to 8, which is the left input of gate 3. And that is why we don't count the output of addition gates in the transcript or tracer computation, because they will be taken care of implicitly by this definition of the capital Lx polynomial using this big summation. Since we are summing them up in this big summation automatically. So with all of these kind of evaluations, the role of this capital Lx is essentially selecting the left input of every modification gate when evaluating at different powers of the roots of unity. So that is why it is called the selector polynomial. So with that, then very naturally, we will have two more selector polynomials for the right input and output of every gate. So once we have Lix, the next one we have will be Rix. And we are asking the question, is each Ci the right input of gate J for all J? And again, to give an example, what is R1x? We are asking whether C1 is the right input of each modification gate. And clearly, this is not the right input of gate 1, not the right input of gate 2, and not the right input of gate 3. So we put 0 and 0 and 0 there. And again, we interpolate this polynomial at the same known set generated by the root of unity, and we have a unique monic polynomial with degree 3 for R1x. Similarly, we're going to do it for R2x, R3x, all the way to R9x. And we have this another table for the selector polynomial Rix that corresponds to the right input of every gate. After that, we can define a capital Rx in a similar way as the capital Lx. And we are summing up Ci times Rix for I equals to 1 all the way to 9. And once we do that, we can actually evaluate this capital Rx at different powers of the root of unity. And what is R of omega? Again, we are looking at the first column of this table. And there's only one non-zero in this column, that is R2x, simply because C2 is the right input of this gate 1. And because of that, in this entire summation, there's only one non-zero term, that is C2. So we are selecting C2 out of this trace of the computation. And similarly, if you evaluate R at omega square, that is C3 plus C4, because there are two non-zeros in the second column of this table, and they correspond to the right input of this gate 2. Again, they go through this addition gates, and both of them are right input of this modification gate 2. And finally, we have there's a typo here, should be R of omega to the cube, that equals to C5 plus C6. And that is because we have R5x and R6x to be non-zero at this point, and that corresponds to the right input of gate 3. So we are essentially selecting the right inputs of every multiplication gate using this capital Rx polynomial. Finally, we have the selector polynomial Oix for the output of each gate. Right? And then again, using example, what is O1x? We're asking, is C1 the output of gate 1, gate 2, or gate 3? The answer is no for all of them, so we have a vector 0, 0, and 0, and 0. And we're going to interpolate this polynomial and get a unique polynomial of degree 3. And finally, we just have this entire table that corresponds to the output of every gate, defining the polynomials Oix. And we have the definition of this capital O of x as the summation of Ci times Oix using this table. And for a similar reason, when you evaluate this Oix at different powers of roots of unity, it's essentially selecting the output of each multiplication gate. And so O of omega equals to C7 because there's non-zero, and that is the output of this gate 1. And O of omega square is the output of gate 2, O of omega cube is the output of the gate 3. So that completes the definition of these three sets of selector polynomials. Okay. So once we understand the definition of these selector polynomials, we are almost there to understand this entire construction of the QAP. And the last piece of the puzzle is this master polynomial, P of x. So I'm going to define a polynomial P of x as the product of Lx times R of x minus O of x. And if you can, if you expand the definitions of these polynomials, we have an equation consisting of three big parentheses. In the first parenthesis, this is the summation of Ci times Lix times the summation of Ci times Rx minus the summation of Ci times Oi of x. That is the definition of this so-called master polynomial P of x. Once we have that, the claim is that the P of x should evaluate to 0 at all powers of this root of unity, defined by this public predefined set. And why is that? Let's take a look at the definition of these polynomials using this example. Right? So we've actually went through all of these evaluations of Lx, Rx, and Ox. So what is P of omega? Well, that equals to L of omega times R of omega minus O of omega. Okay. So then what is L of omega? From previous slides, we know that it's basically selecting the left input of gate 1. And that should equal to C1 because of the definition. And similarly, R of omega is selecting the right input of gate 1 and equals to C2. And O of omega is selecting the output of gate 1, which is C7. So then P of omega simply equals to C1 times C2 minus C7. That equals to 3 times 2 minus 6. And it should be 0 in this example. Right? It's exactly taking the left input of multiplication gate times the right input of multiplication gate minus the output of a multiplication gate. And if this trace is correctly computed by evaluating the circuit, then it must be 0, because left times right minus the output should equal to 0 for the first multiplication gate. Then for a similar reason, let's take a look at P of x evaluated at omega square. Again, by the properties of these selector polynomials, we're essentially selecting the left input, right input, and output of gate 2. So the equation becomes C7 times C2 plus C4. We are taking account of the addition automatically in the definition, minus C8. And if you do the calculation, clearly this is a 0 again. So P of x equals to 0 at omega square. And finally, P of omega cubed should also equal to 0, because we are taking the left input of gate 3 times right input of gate 3 minus the output of gate 3, and that should equal to 0. So because of that, we can see that as long as this Ci is the correct evaluation of the circuit, is the correct trace of this computation, then P of x should be 0 for omega to the power of j for all j equals to 1, 2, and 3 in this example. So finally, how can we actually show that a polynomial P of x equals to 0 at the given locations? What is an equivalent condition? So again, this is not saying that P of x is a 0 polynomial, right? Because the degree of P of x is actually twice of the degree of Lx, and in this case, the degree is 6. So this is clearly not a 0 polynomial. So this condition is equivalent of saying to saying that P of x can be written as a product of two polynomials, Vx times the quotient polynomial Q of x, where Vx is the vanishing polynomial, defined as x minus omega times x minus omega squared times x minus omega to the cube. And this polynomial evaluates to 0 at all these 3 points in this set, because there's the roots of these 3 points. So that is why it is called the vanishing polynomial, because it vanishes to 0 at all elements in this set. So basically, you're just taking the product of x minus each element in the set and multiply them together. That is the vanishing polynomial of a given set. And this polynomial is the polynomial of minimum degree that equals to 0 at these given points. And also it should be a non-zero polynomial. So then any polynomial that equals to 0 at these points can always be written as the product of this vanishing polynomial times the quotient polynomial with the corresponding degree. So that is why if we can write p of x as v of x times any quotient polynomial q of x, it is equivalent to say that this p of x evaluates 0 at these given points. So that is the property using the vanishing polynomial. So that completes the entire story of this QAP. So that is the design of this quadratic arithmetic program. So to sum it up, essentially, we're trying to reduce the problem of this circuit satisfiability to an equivalent problem that can be represented as a polynomial equation. And so that later we can use cryptographic tools to compile it to an efficient SNARK in practice. In particular, in this case, P is trying to claim that he knows the witness such that C of xw equals to y. And through this entire definition of selector polynomials, the master polynomials, and vanishing polynomials, it is equivalent to say that the prover P claims to know a vector C, which is a trace of this computation, such that this master polynomial P of x can be written as V of x times Q of x. And they are equivalent conditions. As long as you can do this, it means that this vector C is the correct trace evaluated using the circuit. So to make things a bit more general, so we have two parameters that are related to the size of the circuit. So first we have this parameter m that denotes the size of this vector, the trace. That's essentially the number of inputs plus the number of outputs of the multiplication gates in the circuit. And in the literature, it is also called the extended witness, because the witness of the prover should technically be the secret input of the circuit. And the prover is evaluating this entire circuit to get this trace of the computation, and that is why it's called extended witness. Another parameter we have is the small n. That is number of multiplication gates, and is also the degree of each selector polynomial, because they are defined by the polynomial interpolation at the locations, the size of which is the same as the number of multiplication gates. So we have two parameters m and n, but they're not exactly the same, but they're on the same order. So m is the number of inputs plus the number of multiplication gates, and n is the number of multiplication gates. So they're off by the number of inputs in this example. Okay. So then again, to visualize it using this big table of selector polynomials defining the QAP, so we have these selector polynomials LIX, RIX, and OIX. The number of rows in this table is m, the size of this extended witness. For every value Ci, we have a corresponding LIX, RIX, and OIX. And the degree of each polynomial is this small n, the number of multiplication gates in the circuit, because we are defining the evaluations that this set of elements generated by different powers of the roots of unity. So the total size of this table is roughly speaking on the order of n times m. It's quadratic in the size of the circuit. But as you can see here, the table is quite sparse, right? We are asking the question whether each value is the left input of a gate or not. And if you think about it carefully, the total number of non-zeros here is linear in the number of multiplication gates in the circuit, or linear in the size of this circuit. And you can't have a circuit with all ones in the table. So because of that, there exists a sparse representation of this entire table. And another important property to highlight here is that this table is a public information. It does not depend on any values or this witness in the circuit known by the prover. They're solely defined by the structure of the circuit, whether each wire connects to a certain gate or not. So because of that, this table can be generated in a pre-processing phase, which is actually important in the construction of the real SNARK. Okay? So that's why in this equation defining the master polynomial, I'm using this blue color to represent those polynomials which are known both by the prover and the verifier. So they are public information and can be pre-computed with a sparse representation And the secret value only known by the prover is these CIs. So they were actually derived from the witness, the secret input of the circuit, and the prover evaluates this entire circuit and they get this extended witness of CIs. And this QAP, the prover is trying to convince the verifier that the CIs satisfy this set of equations. Right? This P of x can be written as the vanishing polynomial V of x times the Q of x, where the vanishing polynomial is again a public information, and this quotient polynomial is a secret information known only by the prover. So in this way, we complete the description of this entire QAP. So essentially, we are reducing the problem of a circuit satisfiability to a quadratic arithmetic program, showing that the polynomial P of x has this property that can be decomposed as V of x times Q of x, and they're equivalent with each other. As long as there exists such a CI passing this check, then it means that the circuit, the prover knows the assignment of the circuit that can be satisfied and give you this corresponding output. So that is quadratic arithmetic program. Welcome back. In the second segment of the lecture, I'm going to show you how to compile a quadratic arithmetic program to a SNARK with a constant proof size using cryptographic tools. So before showing you the detailed construction of the SNARK, I want to explain a little bit more about the model of a linear PCP. So first, they have this classical model of probabilistically checkable proofs, in which the prover can actually generate this PCP oracle, and you can think of it as a big message of a polynomial size. And instead of sending it directly to the verifier can actually make several point queries, asking what is the elements of this big vector. And with this point queries, the verifier is able to verify the correctness of the computation, or the prover knows the satisfying assignment of the circuit efficiently. And this was a big breakthrough in the complexity theory, and then the early SNARK constructions of Killian and Micali were based on this PCP model. Essentially, they're compiling the probabilistically checkable proofs into a real SNARK using Merkle trees on top of this PCP oracle. So instead of sending this PCP oracle directly to the verifier, the prover can commit to this PCP oracle using the Merkle tree and sends only the root of the Merkle tree to the verifier. And later, to answer these point queries, the prover additionally attaches the Merkle tree proof to the verifier with logarithmic size in the size of the PCP oracle. So in this way, they were able to build asymptotically good SNARKs for a large class of computations. So then, in analogy to this classical PCP model, there are several generalizations of the model that we've learned in previous lectures. So the first one is the interactive PCP proposed by Kalai and Razi in 2008, and also the interactive oracle proofs proposed by Ben-Sasson, Chiesa, and Suner in 2016. So in this model, instead of sending a single oracle, the prover can actually interact with the verifier and sends multiple oracles during these interactions. And note that it's only interesting with the interactions, otherwise the prover can just send all of these oracles together as in the original PCP. And after that, the verifier can make point queries from all of these oracles and then check the correctness of the computation. And this IOP is actually the model used in the Fry protocol explained in the previous lecture. And again, we can compile an IPCP or IOP to a real SNARK system using Merkle trees. And this Merkle tree is again the cryptographic primitive we use. So we're going to build a Merkle tree on top of each oracle and then sends the Merkle tree proofs for these point queries. And again, this generalization improves the efficiency of these oracles and the prover time significantly in practice. Another generalization we've learned before is this polynomial IOP. For example, it was used in the Planck system. And the polynomial IOP was formalized by Boonsfish and Spinek in 2020 in the DARK paper. So in this model, instead of sending a string as in the original PCP, the oracle is a polynomial generated by the prover. And the verifier can make evaluation queries on chosen points of the polynomial, and the oracle replies with f of r to the verifier for the verifier to verify the correctness of the computation. And then in order to compile it to a real SNARK, we have these polynomial commitments as we learned in the previous 2 to 3 lectures. And so instead of sending the polynomial to the verifier or post it on the fly, the prover commits to the polynomial and open it at these points using the polynomial commitments. So again, we have the components of polynomial IOP and then the polynomial commitments of the cryptographic primitive. So then in analogy to all of these models, here's the model of a linear PCP. So again, it's a generalization of the classical PCP model and was proposed by Ishai, Kushlevsky, and Ostrowski in 2007 paper. So in this linear PCP model, the oracle generated by the prover is a linear function. So you can think of it as an oracle defined by, for example, vector C. And again, instead of sending it direct to the verifier can make queries to this oracle. And now the queries are actually linear functions. So the verifier can submit again a vector, let's say Q1, of the same size as C, for example. And the oracle will compute the inner product between this C and the verifier's query Q and return a single value to the verifier. So this defines a linear function for the oracle and the query. So that is why it's called linear PCP. So the prover is only allowed to post these linear oracles, and verifier is only allowed to make linear queries from these oracles. So that is the linear PCP model. So then the quadratic arithmetic program I explained in the first part of the lecture can actually be categorized as a linear PCP in exactly this model. And here's the reason why. So recall that in the quadratic arithmetic program, we are trying to, the prover is trying to convince the verifier that this master polynomial computed using the extended witness CI and the public selector polynomials LIX, RIX, and NOIX can be written as the product between a vanishing polynomial, again this is public, and the secret quotient polynomial Q of X. And then we show that this is equivalent to circuit satisfiability. So then in order to show this, we can actually apply the linear PCP model. And this linear PCP oracle is simply the extended witness C and also the coefficients of this Q of X. Then with this oracle, one way to check this equation is again evaluating it at a random point. Right? So the verifier can compute this evaluation of this polynomial equation at the random point gamma. And to do that, the verifier can only submit linear queries to this oracle. And the first query is the inner product between C and the evaluations of Li at the random point gamma. And here I'm abusing the notation informally to use this bold letter to denote the vector for all I, like L1 gamma, L2 gamma, and so forth. So then the value in the first parenthesis is simply the inner product between C and Li gamma. And similarly, the second component is again inner product between C and the second query from the verifier. And then we have C, the inner product between C and the third query from the verifier. And then finally, V of gamma can be evaluated locally by the verifier, and Q of X, the evaluation of Q of X can be viewed as an inner product between the coefficients of Q and this vector generated by the random point gamma. So in this way, the verifier can actually check this equation using 4 linear queries to this linear PCP oracle. And if this equation is true, then by the Schwarz-Zippo lemma, we know that with high probability, this polynomial equation on the master polynomial is also true. So this gives you one way to check the validity of this master polynomial of a quadratic arithmetic program in the linear PCP model. So that is why QAP is actually an instantiation of a linear PCP. But note that here, in the real product that I'm going to present next, we are not using this random queries and not using Schwarz-Zippo lemma. We are using another cryptographic tool to do it, as I'm going to show you right now. So that is the model of a linear PCP. So what I'm going to do next is, again, in analogy to the classical PCP, polynomial IOP, and the IOP and IPCP. Right? So right now we have the quadratic arithmetic program, that is the information theoretical component in the linear PCP model. And next, I'm going to show you how to compile it to a real SNARK with a constant size proof using the cryptographic tools. So the cryptographic primitive we are going to use is actually our old friend, bilinear pairing. And recall that in lecture 6, I explained this definition of bilinear pairing and used it to construct the KZG polynomial commitment. And here we're going to use it again to construct this SNARKs based on linear PCP and quadratic arithmetic program. So in bilinear pairing, we have these parameters of a bilinear group, where this G is the base group and the GT is the target group, and both of them are of order P. And small g is the generator of the base group. And there is a key operation called bilinear pairing. It takes two group elements in the base group as input and computes one element in the target group. And the rule of this computation is basically computing the multiplication in the exponent and then bring it to the target group. And as an example, the power of this bilinear pairing is actually to verify the correctness of the product in the exponent. So given g to the x and g to the y, a pairing can check that if some element h is g to the xy or not without knowing x and y. So that is the tool of bilinear pairing we are going to use. So now let's see how can we use this cryptographic primitive to compile the QAP into a real SNARK with constant size proof. Again, here I'm showing you the master polynomial we're trying to check. And again, to emphasize, these CIs are secret values, extended witness, known only by the prover. And these LIX, RIX, and NOIX, these are public selector polynomials defined by the circuit, and they're known by both the prover and the verifier, and they can be computed in a preprocessing phase because they only depend on the circuit, but not on any secret value. And similarly, we have the public vanishing polynomial V of x, and this quotient polynomial is computed, for example, through the polynomial division and is only known by the prover. So then instead of sending these CIs and Q of x directly to the verifier, as in the linear PCP model, here's what we are going to do. There is a setup phase of this SNARK based on a quadratic arithmetic program. So in the setup phase, first we are going to generate the parameters of a bilinear group, and then computes this set of public keys. And in this case, we're calling it as a proving key that will be used by the prover. So this proving key is basically evaluating each selector polynomial at a secret evaluation point tau chosen by this preprocessor. So we're going to compute g to the li tau, g to the ri tau, and g to the oi tau for all I from 1 to n. And note that these are the selector polynomials, LIX, RIX, and OIX, evaluated at location tau and raised to the exponent of g. Then the second half of the proving key, we're going to evaluate g to the tau, g to the tau square, and so forth, all the way to g to the tau to the n. And note that this is exactly the same global parameters as in the KZG polynomial commitments, and also as in the Planck or Marlin SNARK systems. And this is the same kind of trusted setup process as these SNARKs. But in addition, in order for the SNARKs based on QAP or linear PCP to work, we also need these additional terms in the proving key as shown on the slide. And these proving keys depend on the circuit. They're defined by the selector polynomial, which are again defined by the connections of the circuit. And that is why this preprocessing phase is circuit dependent. And for every computation you're trying to prove, you have to generate a different set of proving keys. And then we have a verification key, which is g to the power of v evaluated at tau, where v is the vanishing polynomial. And that is known by the verifier. After this, the most important step is we have to delete this tau completely. And that is why this is called the trusted setup, and it's circuit dependent. So that is the key generation algorithm of the SNARK. So next, let's see why we are generating this set of public keys. How can we use them to compress the prover's messages of these extended minutes and the quotient polynomials. So the way to do it, or the key idea, is to actually compute each term of this master polynomial in the parentheses using the evaluation at the secret location tau and raised to the exponent of g. So in the first element in the proof, we are going to compute pi1, which equals to g to the power of summation ci times ioi tau. And if you take a look at this, the term in the exponent of g is exactly the first polynomial in the first parenthesis evaluated at the location secret point tau. And so that is pi1. And again, following the same derivation as shown in the K3 polynomial commitment, this pi1 can be evaluated by the prover without knowing the secret key tau. It can be computed using the public parameters g to the power of ioi tau. So essentially, you're raising each term of g to the ioi tau to the corresponding coefficient ci in the extended business, and then multiply them together, you can get a single element pi1. Then similarly, the prover is going to compute pi2 using the polynomial in the second parenthesis. So that is g to the power of summation ci times ri tau. And this can be evaluated using the second set of public key. And then we have pi3 that equals to g to the power of summation ci times oi tau. And finally, we have pi4, which is equal to g to the power of q tau, where q is the quotient polynomial. And this can be evaluated using the last set of public parameters in a similar way as the K3 polynomial commitment. Just raise each key to the corresponding coefficients of this polynomial q of x. So in this way, the prover generates 4 group elements as the proof to the verifier. And that's the proof algorithm in this SNARK. So finally, how can the verifier verify the correctness of this computation? So again, the idea is to actually check the correctness of this equation, the master polynomial equals to v of x times q of x, in the exponent. And so we already have all of these terms in these 4 proofs, and we merely need to check the relationship, the product relationship, as shown in this equation. And in order to do that, we need a bilinear pairing operation. And here's the equation to check it. The verifier is going to compute the pairing between pi1 and pi2. And here, if the prover is honest, then the pi1 and pi2 will be computed as shown on the slide. Then the pairing between them will give you the product between this value and this value, which is exactly the same as the product of the first polynomial in the first parenthesis and the second polynomial in the second parenthesis, as in this polynomial equation, evaluated at the point tau. And then the verifier is going to divide it by the pairing of pi3 and the g itself. So that gives you subtraction in exponent by the summation of ci times oi tau. And that is the third term in this equation. Finally, on the right-hand side, the verifier is trying to compute v of x times q of x evaluated at this point tau. So how can we do that? Again, by linear pairing. And the verifier is going to compute the pairing of g to the v of tau, which is given as a verification key, and also is a known information, with pi4, which is generated by the prover. And again, if the prover is honest, this is g to the q of tau, and the right-hand side gives you g to the v of tau times q of tau in the exponent in the target group. So then if following all of these derivations, that gives you the first polynomial times second polynomial minus the third polynomial equals to vx times q of x, all evaluated at its secret location tau in the exponent. So that is why the verifier can actually check this master polynomial equation using the bilinear pairing. And again, the reason why we need bilinear pairing is we are checking the product relationship in the exponent. And without bilinear pairing, the verifier is not able to do that because of the computational Diffie-Hellman assumption. So that is the complete description of this SNARK protocol. And actually, this version of the protocol is not the real version. It's actually not secure. But the reason why I'm showing you this first is already highlights the key idea of this construction of the SNARK based on QAP. So in the next part, I'm going to show you several problems of this version of the protocol, and also how to fix these problems to get the real SNARK protocol. But just for your information, these changes won't affect the key ideas and also the complexity of this SNARK protocol. So let's do that one by one. So the first problem of this protocol is, we already explained, if the prover is honest, then all the derivation follows and you can actually pass the verification. But now what about security, right? If the prover is malicious, is the protocol secure? Well, I'm not going to go into the formal security proof. These are actually quite technical, and you can refer to the original papers for the real security proof. But I would just highlight certain intuitions about the problems. And the first problem is, how can we make sure that a malicious prover is really using this set of public parameters to compute these proofs? We have these nice structured public parameters in the proving key, but there's no guarantee that the prover is using them to compute pi1. But what if the prover is computing this pi1, pi2, pi3, pi4 just using some random numbers and it happens to pass this verification? And then there's no guarantee that the prover is really proving the satisfiability of the circuit. So then the solution is actually some techniques we've learned before in the KZG polynomial commitment, either using the knowledge of exponent assumption or the generic group model. So to remind you a little bit, so in the knowledge of exponent assumption, for every proof you are trying to compute using a set of public keys, we are going to generate an additional set of public parameters using a secret number alpha, and then compute g to the alpha times Li tau. So it's a counterpart of the original public parameters. And then for every proof pi1 you want to, the prover is trying to generate, we also ask for a counterpart pi1 prime, generated using the second set of public parameters. And with that, the verifier has an additional check, is using bilinear pairing. She's going to check the pairing of pi1 and g to the alpha, where g to the alpha should also be part of the verification key, and I'm omitting here for simplicity. The pairing of these two should equal to the pairing between pi1 prime and the generator g. And if the prover can pass this verification, then by the knowledge of exponent assumption, the prover has to compute pi1 as g to the power of Li tau times some coefficients chosen by the prover. So that is the knowledge of exponent assumption. And if you apply this to all of the proofs in the vanilla version I described before, we can actually solve this first issue. And this is used in this PGHR 13 paper in the Pinocchio construction. Another solution is, again, discussed in the KZG polynomial commitment, called generic group model. So here we don't need to do any additional check. So this is a different model, and informally speaking, the adversary is only given an oracle to compute the group operations. So that is why given g to the power of Li tau, sorry, there's a typo, should be g to the Li tau without alpha. The adversary can only compute their linear combinations, meaning that the adversary cannot just generate a random number and happens to be a group element on the curve. So because of that, in the GGM model, informally speaking, the adversary has to use these global parameters, the proving key, to generate the proof. And this solution is used in Gross 16. And again, the real proof is much more involved, because the adversary not only has access to these public parameters, it also has access to other parts of the public parameters, and you have to use some tricks to formally prove that you can actually extract the coefficients from the proper coefficients from the adversary. But this is the high-level idea to solve the first problem, making sure that the adversary is really using the public keys to generate these proofs. So that's the first patch towards the real protocol. Then the second problem is somehow related to the first problem. So with the knowledge of exponent assumption and GGM, we can make sure that the prover is using the public keys to generate these proofs. But there's no guarantee that the prover is using the same coefficient, the same extended witness, to compute pi1, pi2, and pi3. So here I'm showing you the original version, the vanilla protocol protocol that I described before. Note here that pi 1, pi 2, and pi 3 are supposed to be computed using the same set of CIs in order to make sure that it is the equivalent version of the quadratic arithmetic program to the original circuit satisfiability. Even with KOE or GGM, you can only make sure that pi 1 is computed using this g to the power of Li tau times some elements. And pi 2 is g to the power of Ri tau times some elements that could be potentially different from pi 1. That's the only guarantee you have from KOE or GGM. And if you only use these checks, this protocol is not secure. That is because if we allow the prover to use different vectors in the computation of pi 1 and pi 2, this is not corresponding to the original circuit satisfiability problem. Now, the quadratic arithmetic program is this master equation is saying that if and only if the prover is using the same CIs in these computations, this is equivalent to the original circuit evaluation, circuit satisfiability. And intuitively speaking, you can see the reason as follows. So these are selector polynomials, as I explained before, by selecting left input, right input, and output of the circuit. So the master polynomial only makes sense if the prover is using the same CIs for the selector polynomials to select from. If the prover is allowed to use different vectors, then the computation is not even relevant to the original circuit. You're selecting some values from one vector and selecting some other values from another vector and selecting some values from the third vector, and then they satisfy a certain multiplication relationship. And this has nothing to do with the original circuit evaluation. So that is the second problem. So how to make sure that the prover is using the same CIs in the computation of these three proofs. So then the solution is to introduce an additional set of public parameters in the proving key. So this set of proving key is g to the power of beta times Li tau plus Ri tau plus Oi tau. Okay? And also we need to include g to the beta as part of the proving key and the verification key. So with this set of public keys, in addition to pi 1 all the way to pi 4, we ask the prover to generate an additional proof, pi 5, which equals to the product of g to the pi beta Li tau plus Ri tau plus Oi tau raised to the power of Ci. And this can be computed using this new set of public keys. Essentially, the prover is raising each element of this public key to the corresponding power of Ci for each element in the extended witness. And that's pi 5, again, a single group element. So what's the purpose of this additional proof and additional proving key? So it turns out there is actually a nice relationship between this pi 1 all the way to pi 3 and pi 5 if these are generated honestly using the same CIs. So you can see here that if the prover is using the same CI in pi 1, pi 2, and pi 3, if we multiply pi 1, pi 2, and pi 3 together, multiplication gives you summation in the exponent, and for each I, there will be a common factor of Ci in the exponent. So because of that, we can actually extract the Ci out of the computation, and that gives us the summation of Li tau plus Ri tau plus Oi tau together times Ci in the exponent. And that's what we're doing exactly here on the left-hand side of this new equation to check. Okay. And on the right-hand side, we have this summation of Li tau, Ri tau, and Oi tau given by the new public key. And then we're going to raise it to the coefficient of Ci. And if the prover is honest, this verification should pass because we have the same kind of Ci times the summation of these Li, Ri, and Oi in the exponent. So that's the purpose of this additional check. And to put it in the opposite direction, if the prover is malicious and is cheating using different vectors in the computation of pi 1, pi 2, and pi 3, then when we multiply these three proofs together, there won't be a common factor for the same I. Right? So there's no way for the prover to express this product as this set of public key is raising to the same coefficient Ci, because you're using different vectors or values in the computation of pi1, pi2, and pi3. And that is why, intuitively speaking, the prover cannot pass this additional check if the prover is cheating. So that is the solution to the second problem. So with this additional check, we can make sure that prover is using the same set of coefficients in the generation of pi1, pi2, and pi3. And that is why it enforces this original quadratic arithmetic program, which is equivalent to the circuit satisfiability problem. Finally, we have the last problem. So far we've talked about the simplified version, where we are assuming that this entire input of the circuit is the witness of the prover. The prover is trying to convince the verifier that he knows a satisfying assignment of the circuit. But in practice, in many interesting applications and computations, we need to have some public inputs that are known both to the prover and the verifier. So then how can we support this general case in the construction of this SNARK? So right now, instead of proving C of W equals to Y, we are proving C of XW equals to Y, where W is the secret witness known by the prover, X is the public input, and Y is the public output. So how can we support this version? Well, it turns out the fix to this issue is actually relatively simple because of the nice algebraic structure of the proof. So in the vanilla version or original version I was describing, each proof, I'm using pi1 as an example, equals to g to the power of summation ci times li tau for all I from 1 to n. So we are summing over all values in this extended witness that corresponds to all the evaluations of the circuit in the output of multiplication gates and the input. When we have some public inputs and outputs, it just means that some wires will have the values that are known by the verifier instead of only secret to the prover. So then we can actually decompose this original proof pi1 into two parts. In the new proof, the first part is only known by the prover, and I'm calling these wires as the set I mid. Instead of all wires from 1 to m, this is a subset called I mid known only to the prover. That includes the secret witness known by the prover and all the evaluations related to this secret witness. And then the prover is going to compute a new pi1 as g to the power of summation over this set of I mid, ci times li tau, instead of summing over I equals to 1 to n. Then after that, we have a second component, which are the public values known by the verifier. And then I call it I of I/O, standing for public input and public output. Then the verifier can compute g to the power of summation I belongs to I/O, ci times li tau. And because of this nice algebraic structure of the proof, if you multiply pi1 with the new pi1 with the second component, you get the original pi1, because multiplication gives you summation in the exponent. So which means that if you have some public inputs and public outputs on certain wires, the prover is just going to generate this new pi1 as g to the power of I belongs to I mid, ci times li tau. And the verifier can recover this original pi1, I'm calling it pi1 star here, by multiplying pi1 with g to the power of I in I/O, ci times li tau in the exponent. And similarly, the verifier and prover can do the same thing for pi2 and pi3. And I'm omitting the formal equation for them. And I'm just going to call these original pi2 and pi3 as pi2 star and pi3 star. Once we do that, we can just perform the original check. The verifier can perform the pairing between pi1 star and pi2 star divided by the pairing between pi3 star and g, and check if it is the same as the pairing of g to the b tau with pi4, as in the original version. So that's the fix to the third problem. Whenever you have some public inputs or public output, just move these tasks to the verifier side. And because of this nice algebraic structure in the exponent, the proof remains a constant size. And of course, that requires some changes in the key generation algorithm, because the proving key now only includes these public parameters that corresponds to these intermediate values known only by the prover. And the verification key now needs to include these wires for the input and output. So that's the patch for the third problem. With all these three patches, we end up with the formal protocol of this of a real SNARK constructed from the quadratic arithmetic program. And this version is actually was actually proposed by the Pinocchio paper in PGHR 13. Okay? And here I'm listing the formal algorithm to put everything together. Okay? And as you can see here, in the key generation, we have the proving key, which is g to the power of these selector polynomials, and also another term to make sure that the prover is using the same set of coefficients to generate all the proofs for all I for the wires owned by the prover, known by the prover. And we also have g to the beta and g to the tau, g to the tau square, and all the way to g to the tau to the m to evaluate the quotient polynomial. In the verification key, we have g to the v tau as I specified in the vanilla protocol, and we also have the additional verification key that corresponds to the wires that are known publicly by the verifier. And in order to generate the proof, the prover computes this pi1, pi2, pi3, and pi4 for these polynomials in this master polynomial equation of QAP, and also pi5 to show that the coefficients of these terms are the same. And to verify the correctness of this proof, the verifier first computes the pi1 star, pi2 star, and pi3 star, and then check these two pairing equations. And if these checks are true, then the verifier knows that the prover is computing the circuit evaluation correctly that satisfies the quadratic arithmetic program equation. So that is the formal description of this SNARK based on QAP. So finally, to see the properties of this SNARK, again from the Pinocchio paper, the scheme has a per circuit trusted setup phase. The public keys are dependent on the connections of the circuit because of the selector polynomials. And if you still remember the big kind of table for these selector polynomials, technically speaking, the total size is quadratic, but there is a sparse representation because of the sparsity of the matrix, sparsity of the table. So because of that, there is an efficient algorithm to generate all of these public parameters in linear time in the number of, in terms of group exponentiations, in the number of size of the circuit. And to generate the proof, there are two main components of the prover algorithm. First, the prover has to run this FFT algorithm to interpolate these polynomials and compute polynomial multiplications and divisions as I described in the QAP polynomial equation. After that, the prover needs to compute the linear number of group exponentiations in the size of the circuit to compute these proofs by raising each public key to the corresponding power of the coefficients and multiply them together. And the main power of this SNARK construction is that it has a very short proof. The proof consists of a constant number of group elements in the base group. So in the version I described in Pinocchio, it has only 5 group elements that is secure in the GGM model. And in practice, it is only hundreds of bytes. That is kind of one of the shortest proof size among all the SNARKs. And the verifier time is also very efficient. If we ignore the part for dealing with input and output, the verifier time is only constant. It's like constant number of pairing equations and bilinear pairing operations. And currently speaking, it's very efficient, less than 1 millisecond. But to be precise, the verifier also has to compute the linear number of group exponentiations in the number of public input and output. So in practice, this part can be a little bit more costly for the verifier, but there are additional optimizations to further improve this part. For example, if your input and output is really big, you can actually compute the hash of these input and output inside the SNARK. And then in this way, the public input and output of the SNARK becomes constant, and this computation is negligible. And the verifier can actually check the hash outside of SNARK and then verify the SNARK in constant time. So that is the property of this SNARK based on the quadratic arithmetic program. So in the next segment, I'm going to show you some other variants of this SNARK construction based on QAP. So the first thing I want to briefly explain in this last part of the lecture is the R1CS, rank 1 constraint system. So essentially, this is a generalized computation model replacing the arithmetic circuit for this type of SNARKs based on QAP and linear PCP. And it is widely used in practice. So actually, if you understand the construction of these QAPs and selected polynomials, it is actually fairly easy to generalize it to support the so-called R1CS. And let's see how it works. So remember, in the example in the first part of the lecture, this is the computation of the arithmetic circuit, and taking the selected polynomial Lix as example, we're essentially asking the question whether each value is the left input of a gate. And if it is, we're going to put 1, and then if it's not, we're going to put 0, and we're going to interpolate it to find the unique polynomial Lix. But then a very natural question is that why do we restrict ourselves to either 0 or 1? Right? We can actually generalize these polynomials to work on any publicly known constant. And then we can still interpolate these polynomials and see what happens for this entire computation system. So then let's do that. So now instead of computing only like the left input times right input minus the output, we can have this generalized constraint in this form. Still, it has 3 pairs of parentheses, something times something else minus something equals to 0. But then inside each parenthesis, we can have actually a linear computation on the entire extended witness. We can select multiple elements from the extended witness and multiply them with some public constant. And then let's see how can we define the selected polynomials for this type of constraint. And then by this equation, let's take a look at the first parenthesis. We are summing up Ci times Lix. So in order to map to this constraint, L1 omega should equal to 3, assuming that this is for the first gate or first constraint, right? And L5 omega equals to 5, and L7 omega equals to -7. And for other Li omega other than 1, 5, and 7, they're all equal to 0. And then if you compute the summation of Ci times Lix, that will give you 3 times C1 plus 5 times C5 minus 7 times C7 in the first pair of parentheses. Similarly, we can define Rix as R2 omega equals to 6, R9 omega equals to 10, and everything else equals to 0. And if you compute the second parenthesis, summation of Ci times Rix, that will give you 6 times C2 plus 10 times C9. Right? And similarly, you can define Oix as O3 omega equals to 1, and then O8 omega equals to -2. That gives you the computation in the third parenthesis. After that, we are going to interpolate these polynomials to find unique selected polynomials with the appropriate evaluations and degree. And after that, everything else remains exactly the same as the original protocol I presented for the arithmetic circuit. The only difference is instead of defining things as 0 and 1, we can define them as any public constant. And in this way, the same system can support this kind of generalized constraint where you have a linear computation on the extended witness times another linear computation equals to the third linear computation. And that is exactly called rank 1 constraint system. And that's it. That's a simple generalization, right? So apparently, arithmetic circuit is can be written as rank 1 constraint system, as we've shown in the previous example. But rank 1 constraint system can support the so-called generalized constraint or generalized circuit, gates in this form. So that is why it's more powerful and more convenient to use in practice. And also another thing to highlight here is that by defining these polynomials properly, we are computing these linear computations, like addition, subtraction, and multiply by constant implicitly inside each parenthesis. So that is why these additions, multiplications, and the scalar multiplications by constant are almost for free in SNARK systems for R1CS. So that's another aspect to optimize for real-world computations. So that is R1CS. And another important kind of property of R1CS that we're sharing is the matrix view of this R1CS. So here, we have some parameters of R1CS. So now M is the size of the extended witness, and N is the number of constraints, the kind of the generalized gates. Okay? So now we can view this extended witness C as a vector, and to compute the value in the first parenthesis, it is equivalent to select values from the vector and multiply them by some public known constant. And this can be done by a matrix vector multiplication. The matrix has dimension n by m, where m is the same as the size of the C. So you're computing the inner product between each row and this vector. So that's essentially selecting values from this extended witness and multiply by public constants. And then you're going to do it n times for n constraints. And similarly, we are going to compute R times C for another public matrix and O times C for the output matrix. After that, the result of these three computations are just three vectors of size n each. Then finally, we're just going to check the first vector times the second vector element-wise equals to the third vector. So that is the matrix view of R1CS. We are computing exactly the same constraint system as I described in the previous slide. Okay? And the reason why it is convenient to view things like this is because we can actually propose new SNARK systems for R1CS following this matrix view. All we need to do is to support these two building blocks, a linear check and a Hadamard product check. Okay? So the approach is to first, for example, for a committed extended witness from the prover needs to prove to the verifier that the matrix vector product gives you another committed vector. Right? And that's a linear relationship because the matrix is a publicly known information. So that is why this is called a linear check. And we can perform the linear check for these three matrix vector products. And after that, the verifier ends up with the commitments of three vectors of size n. And the only remaining step is to check the Hadamard product relationship, which is the element-wise product. Right? The first vector times the second vector element-wise equals to the third vector. And once both checks are true, then we have a valid R1CS system and assignment. Okay? So that is a very convenient view of R1CS and a common approach to design SNARKs for R1CS. And this has been used in bulletproofs, Martin and Spartan and so on for SNARK systems beyond those based on QAPs. So the second variant I want to briefly discuss is this popular construction of a Gross16. So this has the smallest proof size among all SNARK systems with only 3 group elements in the proof. And it is actually indeed based on the QAP from the Pinocchio paper I explained earlier. And here I want to show how can we further reduce the proof size. So recall that the goal is still to check the QAP master polynomial equation. P of x can be decomposed as V of x times Q of x. And recall that there were 5 elements in the original proof. Right? We have the proof pi1 for the polynomial in the first parenthesis, and then pi2 for the second parenthesis, pi3 from third parenthesis, pi4 for the quotient polynomial, and pi5 showing that the prover is computing these proofs using the same coefficients. And turns out we can actually combine the last 3 group elements together using one new group element pi3. And the way is as follows. So first you can see here that pi1, pi2 almost remain unchanged. Right? Pi1 still equals to g to the power of ci times li tau. But in addition, we are going to add alpha to it, where alpha is again a secret key computed in the trusted setup. And g to the alpha should be in the public parameters for both the prover and the verifier. Okay? And similarly, pi2 equals g to the beta plus the original ci times ri tau. And now the pi3 will be changed to to take into account all the remaining checks we want to perform. As you can see here, pi3 equals to g to the power of ci times beta times li tau plus alpha times ri tau plus oi tau and plus v tau times q of tau. So the last term is computing this product of the quotient polynomial as the original pi4 for g to the q of tau. And inside this parenthesis, you have ci times oi tau. So that is for the third parenthesis, and they're combined together. Again, it is actually not hard to see this because you can just move the third term to the right-hand side of the equation and have vx times qx plus the third term. And the remaining term for the purpose of proving that the prover is actually using the same CI. Okay? And the new verifier algorithm becomes the pairing between pi1, pi2 should equal to the pairing between pi3 and the generator times the pairing of g to the alpha and g to the beta, assuming that both g to the alpha and g to the beta are in the verification key now. And the way to see this equation is that if you multiply the exponent of pi1 and pi2, you will have the product of this summation times this summation, that is the original master polynomial equation, right? And that should equal to ci times oi tau plus v tau times q of tau by moving the third term to the right-hand side. So you have these terms in the exponent by this pairing check. Then you have some additional terms. When you multiply the exponent of pi1, pi2, you have beta times ci times li, the summation of this, and that's taken care of by this first term in the new pi3. You also have the cross term alpha times the summation of ci times ri tau, and that's taken care of by the second term of this new summation. And the fact that you're computing all of this using this new public key guarantees that the prover is using the same ci as pi1 and pi2, if you prove it formally. Okay? And finally, you have an extra term, g to the alpha times beta, and that can be checked by computing this g to the alpha, pairing of g to the alpha and g to the beta in the verification key. And this can be done ahead of time in the verification algorithm. So that is the kind of high-level idea to further reduce the proof size from 5 elements to 3 elements only. Okay? And that is the kind of the improvement of Lagrange 16. And again, to be precise, this is actually not the actual algorithm. So this is only the giving the intuition of this new algorithm, combining these 3 elements into one in the new pi3. So the real algorithm you need to take into account the intermediate wires known only by the prover and also the public input and public output. You also need to ensure zero knowledge on top of that. So for the real protocol, please refer to the Lagrange 16 paper for details. So basically, to summarize the properties, you also need to change the key generation accordingly with these new public parameters. And now the proof size becomes 3 group elements only. And depending on the bilinear elliptic curves, pairing-friendly curves you're using in practice, it can be as low as 144 bytes in practice. So that's very impressive. And the verifier time becomes a single pairing equation with 3 bilinear pairing in the check. So these are very efficient in practice. So the last variant I want to highlight is achieving the zero knowledge. So as we've always been doing, so in most of the lectures of this course so far, we always focus on the plain protocol with correctness and soundness. And we don't usually talk about zero knowledge. That is because usually it is not hard to achieve zero knowledge. You just add some randomizer to these proofs to achieve zero knowledge. For example, I showed you a version of zero knowledge polynomial commitment in lecture 6. And here we are actually following a similar idea. So again, I'm listing the original protocol of the Pinocchio construction for simplicity. And I'm only showing you the pi1 all the way to pi4 here. Okay. So again, this version is not zero knowledge for a similar reason as I explained earlier in lecture 6. Right? It is deterministic. Right? Although it's not revealing all the values of circuit because it's only a single group element. But you can infer some information from these proofs. Right? You can make a hypothesis whether all the values are zero in the circuit and check whether the proof will give you the same proof. In this way, you can kind of do this brute force search attack to infer information about the values. And formally speaking, there's no way for you to construct the simulator in the proof to prove zero knowledge. And the way to fix it is to actually introduce some randomizers to randomize these proofs. And on top of Pinocchio, the zero knowledge version is fairly simple. Right? The way to do it is to randomize this value by adding an extra term in the exponent. And again, you can try to add a random number, delta 1, delta 2, and delta 3 in the proofs, but then you realize that will ruin the relationship of these proofs, and the pairing equation to check no longer holds. So then the right way to randomize it is to actually introduce delta 1 times the vanishing polynomial, b of tau, to each proof. Because of that, when you multiply these two polynomials together in the exponent, it is still divisible by the vanishing polynomial because you have a common factor in all of these products. So in this way, with these randomizers, we can formally prove that you can actually simulate these proofs without knowing the real witness of the prover. And at the same time, the scheme is also has the knowledge summaries by the same pairing equation check and a slightly different proof. So this is the idea to achieve zero knowledge in the original version of the Pinocchio paper based on QAP. And for the Groth 16 version, it is slightly different, but still you're trying to add some randomizers to these proofs and still preserving the pairing equation to check. So that's the variant of zero knowledge. So that is everything we're going to talk about for SNARKs based on linear PCP and QAP. And in the next lecture, then we'll talk about the construction of recursive SNARKs. So thank you for listening.